Okay, so good morning. It's good to be back. Uh, so I cannot speak very loudly, so I hope if I speak in this intensity, then it's audible to everyone. Yes, Kevin, thank you very much. I'm feeling much better now. So hopefully it's over. Yeah, and all of you, thanks. And all of you, please take care. It's really bad. So yeah, just stay put. So you can hear me, right? If I speak like this. Okay, thanks. Okay, so yeah, so what I planned is I will keep today's and the next lecture informal. So I will not take the class next Tuesday. I will upload some additional videos maybe from last year. Those are more optional, but those of you who are interested must go through them. So today I will talk about some more applications of max flow min cut, and after that we will talk a bit about the exam part. Okay, so I have made some policy about the exams, so I will float it out to you, then we can have a discussion. Okay, so before we move on to applications, so did some of you or all of you like at least go through the material which had uploaded? So do you have any doubt or any questions about so even if you didn't understand all the proofs in details, but any questions about max flow min cuts in general, something which is unclear? All right. Okay, let's see. So let's talk a bit about that today. Hopefully some of the things will become more clear if they are not already. Okay, so so what we will do today, I will try to cover two applications of max flow and min cut. And the reason I picked these problems, at least the first one, is as you will see that apparently this has no relationship with max flow. In fact, it's almost unbelievable that this problem can actually be solved using the maximum flow problem. Okay, uh, so it's called matrix rounding. It's known by many other names, and the problem is as follows. So suppose I give you some matrix. Okay, so let's just start with an example. So suppose I have the following matrix. So I need a bit of a time to copy this. 3. Okay, so suppose we are given this matrix. So the matrix is on any real number. Yeah, on the real number domain. So each entry is a real number. Okay, and let us also write down the row sums and the column sums. Okay, so this turns out to be 17. This is 11. This is 12. And similarly, the column sums. So they turn out to be 16. This is 10. And this is 14. Okay, so suppose you are given such a matrix, and now the task is to round up or round down the entries of this matrix. So what do I mean by round up or round down? So as you can see, each of these entries has a fractional part. So the task is to either round up these numbers to the next nearest integer, or round down them to the nearest integer which is less than that number. Okay, but the crucial condition is that you have to preserve the row sums and the column sums. Okay, so you cannot violate these sums which are already happening. Okay, so let me write down the problem. So the goal is to round up or down each entry to the nearest integer while preserving row and column sums. Okay, So is the question clear to everyone? Okay. Okay. So how to do this now? So before we go on to algorithms, let me also tell you that so in this particular example, the way I have designed it, yes, Kevin. So so Kevin is asking, is this always possible? So we'll prove that this is always possible. Okay. So so in this example which I'm showing you, all the row sums and the column sums turn out to be integers. So if you add up any row or any column, so I've deliberately picked the numbers in a way that they add up to integers. This problem can even be solved even if that is not the case. So suppose each row sum and each column sum also turns out to be fractional. Even then I can ask the same question, that can I round up or can I round down? But then, of course, after you have rounded up or rounded down, the row sums and the column sums will also turn out to be integers. But the condition now is that those integers should also lie within the corresponding range. So for example, if the row sum is 17.2, then you can round up the row sum to at most 18, or you can round down to at least 17. Okay. So that's a slightly more general version of the problem that can also be solved using very similar techniques. But just to keep the thing simple, I'm deliberately using the example where the sums are integers. Okay. Okay. So is the problem clear to everyone? So कैसे करेंगे ये? In fact, as Kevin is asking that why should we even believe that this is always possible? Why? I mean, this is a feasibility question. Why do you even claim that this is always possible? Okay. So, and now it turns out that we'll be able to solve this question using max flows, okay, which is perhaps even more surprising, right? Okay, so before we go on to actually reducing this problem to max flow, what I should talk about, which I probably did not in either one of the uploaded videos or the previous lecture, is integrality of flow. So I might have mentioned this on the fly, but let me just reiterate this thing. It's quite important. Integrality of max flows. So what do I mean by integrality? So theorem says that if all capacities are integers, okay. So suppose I give you a network, right? Suppose I give you a flow network where all the capacities are integers. This is very important. This is a condition which I need. If this is the case, then this will imply there exists a max flow where all flows are integers. Okay. So what this theorem is saying कि अगर मैं आपको एक network दे देता हूँ जहाँ पे सारे capacities integers है, yeah. In fact, the examples which we saw are of that nature. So all the capacities are integral. Then I claim that the maximum flow, there is one maximum flow in this network, which is also integer, in the sense that every edge will have an integral flow. Okay. So why do you think this? How can we claim this? So can anyone tell me why should this be the case? Let's see how much you have done at home. So the question hopefully is clear to everyone, right? So if all the capacities are integer, then I claim that there exists a max flow, which is also integer numbers on every edge. So why do you think we can claim this? Sum of integers is integers, but what do you mean sum of integer? So I'm claiming that the maximum flow is an integer. So why can't it be fractional? Why can't it happen that the maximum flow, it has some fractional flows on some of the edges? Why can't this happen? So why is it necessarily true that there is one max flow Okay, so Trish is saying if there is no such max flow, then we can create a better max flow. Is that very clear? That's not necessary, right? Better to definitely nahi. I mean, I'm sure we can construct examples where a fractional flow is also optimum. So I'm not claiming that every maximum flow is necessarily an integer. I'm claiming that there is one maximum flow which is integer. Ceiling x, no, but you might be. So let's see. Let's try to find an example where a fractional flow is actually optimum. Okay, let's see if I can make an example like that. ST. Okay, so suppose this is one, this is one, this is one, this is one, and this is one. Okay, or let's say suppose this edge is not there. Uh, okay, so suppose this is not there. Yeah, so now let's say I give a flow of so let's say I define the flows as follows. So I give 0.5 here, I give 0.5 here, and I give 1 here. Okay, is this a max flow? Yes or no? Is this a maximum flow in the network, or can I push more flow from S to T? So okay, how do you convince me that this is the max flow? So what is the crucial argument that you can give me that this is the max flow? Max flow 1 से ज़्यादा नहीं हो सकता. Why is max flow 1? Yeah, again, so because every flow is upper bounded by some cut, right? So if I look at this cut, yeah, if I look at this cut, इसका capacity कितना है? इसका capacity 1 है, right? And this is the minimum cut, in fact. So the max flow is 1, but this is a fractional flow, right? So it's not true that the integral flow is always better than the fractional flow. Does everyone understand this point? So this is not even what I am claiming in the theorem. I mean, this is a perfectly valid fractional flow and it's a max flow. Okay, but the point is there exists an integral flow in this network which is also of the same value. What is that? What is such a flow? Suppose I give some names here. So suppose this is A, this is B. So I claim that एक फ्लो ऐसा है यहाँ पे जिसका वैल्यू 1 है और जो सब एजेस में इंटीजर नंबर्स है. So what do you think could be such a flow? It's very simple, right? Yes, right, right. So basically you can do it in two ways. So either you can let me just show it in a different color. Okay, so either you can push a flow of 1 unit along the path A say BT, that you can do. So you can put a value of 1 here, 1 here, and 1 here. That is one possibility. Or you can push a value of one unit of flow along SBT as well. That is also a valid flow. So there are integer flows as well, which add up to a value of which has a value of 1. Okay. So now you tell me, why is this theorem true? So वो तो सीलिंग विलिंग का कुछ चक्कर ही नहीं है यहाँ पे. So how can we argue? Okay. So it turns out that we need to appeal to the algorithm which we have designed in order to prove this. Okay. So what kind of a flow does Ford-Fulkerson give us? Can it give us a fractional flow? So the question is, can FF algorithm produce a fractional max flow? So we know that Ford-Fulkerson algorithm gives us a maximum flow. That we have already, okay, so we have talked about the algorithm, there is a proof that this is true. But the question is, ये जो Ford-Fulkerson algorithm है, can it produce a fractional flow? And if not, then why? Okay, so here is the crucial point, right? So let us remember the Ford-Fulkerson algorithm. So how does the Ford-Fulkerson algorithm work? So it begins with a flow of 0 on every edge, right? So 0 is an integer and all my capacities are integers. Now, what is Ford-Fulkerson doing at every iteration? Well, at every iteration, it is creating a residual graph. Okay, so what is a residual graph? Well, jitna flow abhi hai har ek edge mein, the original capacity minus that flow is the residual capacity. And there are these reverse arcs, remember, which has a capacity that is equal to the current flow on this edge. Okay, but everything so far, so at the beginning, everything is an integer because I am just pushing zero flow from S to T, right? Now, by induction, suppose in any iteration, the current flow is an integer. So if the current flow is an integer and all the capacities are integers, तो next iteration में जो flow मैं push करूंगा, that is also going to be an integral flow, right? There is no way that Ford-Fulkerson can push a fractional flow in any of its iteration. Okay, so this is just a simple inductive argument that because I begin with an integral flow, that is flow of 0 on every edge, और मेरे सारे capacities integers है, right? So Ford-Fulkerson always pushes an integral flow in every iteration. Yes. Okay. So the answer to this is no, since FF algorithm always augments the current flow with an integral flow. Okay, and I know that Ford-Fulkerson indeed ends up with a max flow. So these two together proves that अगर आपके सारे capacities integers है, okay, this is very crucial. अगर capacities fractional है, फिर तो fractional हो सकता है. That we cannot claim. But अगर सारे capacities integers है, so then the maximum flow in this network is necessary. There is necessarily a maximum flow, which is integer. Okay, so the correctness of Ford-Fulkerson is actually a proof of this fact. Okay, questions? Everyone understands this point, or is it too confusing? Okay, so all the applications that we will talk about crucially depends on this fact that जो flow आप compute करोगे, that flow is going to be an integral flow. Otherwise, you cannot solve bipartite matching, for example, using max flow, right? So think about it. So if you think of the bipartite matching application, we are using max flow to solve that problem. But if your maximum flow is integral, then it does not translate to a matching. It has to be an integral flow, right? So that's very, very crucial to understand. Okay, great. ठीक है. So this is one theorem you should always keep in mind. Okay, that if capacities are integers, then there is one maximum flow which is going to be an integer. Okay. So let's now try to solve our original problem. Yeah, this matrix rounding problem. So what we are claiming is कि भाई we can round up or round down so that I can preserve the row sums and the column sums, and I only round up or round down to the nearest integer. ऐसा नहीं कि 3.14 को आप 5 कर देंगे, या तो आप 4 कर सकते हो, नहीं तो 3 कर सकते हो, ठीक है, ज्यादा इधर उधर नहीं कर सकते. Okay, so the first step would be to do a transformation. So step 1 would be to do a transformation. Okay, let me copy this thing. Okay, great. Okay, so first, in order to be able to reduce this to max flow, I'm going to do a transformation. What I will do is I will write another matrix, but I will ignore the integral component of every entry. Okay? So what I will do is I will transform this to another matrix. So if this matrix is A, I will write a matrix A prime, where I will only keep the fractional component of every number. तो जैसे 3.14 हो गया, उसका मैं बस 0.14 रख दूंगा, ठीक है? So it's going to look like this: 0.14, 0.56, 0.3, 0.62, 0.24, 0.2, 0.24, 0.52. ठीक है? So all I did is I am ignoring the integral part of every number. Okay. So why do you so why do you think I did this? Okay, the reason I did this is because now all I have to do is ये जो fractional numbers है, right? इनको मुझे either 1 करना है या तो 0 करना है. ठीक है? So if I in my final solution, suppose for example 0.14 is rounded down to 0, that directly translates to the fact that this number will be rounded down to 3. For example, if 0.56 is rounded up to 1, right, then it translates to the fact that this number will be rounded up to 7. Okay, तो ये जो ट्रांसफॉर्म मैट्रिक्स है मेरा, इनको राउंड करके अगर कोई एंट्री 0 हो गया तो मैं ओरिजिनल एंट्री को राउंड डाउन करूंगा. अगर ये 1 हो गया तो मैं ओरिजिनल एंट्री को आई विल राउंड इट अप. That's the semantics of the new matrix A prime. Is this clear to everyone? Okay. ठीक है? Right? Okay. Now let's again write down the row sums and the column sums. Now it's not clear. Okay. ठीक है. I will explain it again. So it turns out that this is 1 in every case. It is more of a coincidence. ऐसा जरूरी नहीं है. ठीक है? Okay. So Harsh is not clear about this. So what I'm saying is, remember, ultimately your task is to round up the original numbers or round down the original numbers in the matrix A, right? So now I have transformed this to a problem where I'm ignoring the integral part, okay? And I'm only writing out the fractional parts. Now what I'm saying is that it's enough for me to round up these numbers to either 1 or 0. ये जो fractional numbers है. Why? Because if I round up somebody to 1, that directly translates to rounding up the corresponding entry in A. So for example, if I round up 0.56 to 1, then that means that you will round up 6.56 to 7. Okay? On the other hand, if you round down 0.3 to 0, then it corresponds to rounding down 7.3 to the last integer, which is 7. Okay? And you can verify, right, that if I am able to do the rounding of this transform matrix while preserving the row sums and the column sums, then this directly translates to also preserving the row sums and the column sums in the original problem. Okay? Yeah, is it clear now? Right. Okay. Any questions about this? Yeah. Okay. So now the question is, how do I solve this using max flow? So any idea? Just wild ideas of how do I do this using max flow? What kind of a graph should I create? What do you think is a graph that I can create in order to be able to solve this problem? What is the flow network that I can create? Yeah, let's try to be just creative. Okay, yeah, it's not at all obvious. Edges along rows and columns. So Kevin, what do you exactly mean? Use the row and column sums as capacities. Very, very good. Okay, very good. So what these people are suggesting is, why don't I use because I have to preserve the row sum and the column sum. So why don't I use those as my capacities? So that is the amount of flow that I want to send in some sense. But before that, what are going to be the vertices in this graph? What should they represent? So what do you think should the vertices in this graph represent? Or what kind of a graph should this be? Yeah, yeah, this is similar to matching, so that's a hint. Okay, Vishwajit. So you want to keep a vertex for every entry in the matrix. No, that is going to be messy. Because see, ultimately, see, the reason that is not a good idea is because you have to, so when you try to reduce some problem to a flow problem, you have to understand what are the constraints that you are trying to impose. देखो यहाँ पे तुम्हारा constraints है row sums and column sums. You don't really care too much about the individual entries because those can be rounded up or rounded down. In fact, that is what you want. The problem statement. हाँ, तो problem statement अभी ये है कि तो ठीक है. Now let me define the problem statement in this transform matrix. So Soham, this transform matrix is a matrix where each entry is a fraction between 0 and 1. ठीक है? So what I want to do is I want to either round up the numbers to 1 or round down the numbers to 0. But the condition is that every row sum and column sum needs to be preserved. जैसे यहाँ पे सारे row sums और column sums 1 है, which is by the way a coincidence. It's not necessary. Okay? ये ज़्यादा भी हो सकता है, but it's an integer. So I have to round up or round down in a way that these sums are preserved. नहीं तो मैं तो arbitrarily round कर सकता हूँ, right? I mean, I can even round up everybody to 1. That is also a rounding up, but that will not preserve the row sum, for example, or the column sum. Okay? So you can try various techniques. You can try, for example, rounding down to nearest integer. Excellent, excellent. Okay, so there are some suggestions now. So some people are saying that I will keep one vertex for every row and one vertex for every column of this matrix. Okay, so let's do that. So suppose, okay, Shruti, the sum in A prime would also not be always integer, right? No, Shruti. So the point is, in the kind of examples that we are doing today, यहाँ पे in the original problem the sum is an integer for every row and every column. तो अगर आप उससे कुछ इंटीग्रल पार्ट हटा लिया तो बाकी जो फ्रैक्शन बचा है उसका सम भी इंटीग्रल ही होगा. This is just for this specific type of examples that I am showing you. क्योंकि देखो every row and column sums up to integers, right? Yeah, so we are talking about integral sums today. The other thing requires a, yeah, I will tell you later. Okay. Okay, so here is an idea. So some people are saying ki, let's keep one vertex for each row and one vertex for each column. So suppose the rows are represented by I and the columns are represented by J. Okay, so let me construct this graph. Okay, so these are the rows and these are the columns, right? So they are supposed to represent the rows and the columns. Okay, ab what should be the edges in this graph and what else do I need? I need a source and a sink, right? Because, okay, I want to reduce it to a max flow. So I need a source and a sink. Okay, so Kevin is saying that I should make this a complete bipartite graph. Okay, so I will put an edge. So suppose this is I and this is J. So I will put an edge between every pair of vertices. Okay. Okay, so I'm not drawing all the edges, but you understand this is going to, this is, I want this to be a complete bipartite graph. Okay. ठीक है, तो ये तो हो गया. What about the, so now how do I represent this row sum column sum business? That is something I want to preserve, right? Very good. Okay, so what Kushal is suggesting is ki, let's put an edge between the source and every I, and let's put an edge between every J and every column and T. Okay, and here is the crucial thing. Okay, so let's give some directions. So maybe I give the directions like this. You can also do the other direction as well, right? Doesn't matter. It's the same problem. ऐसा कर दिया मैंने. Now what is going to be the capacities of these edges? Because ultimately, see, I have to define a flow network. So the question is, what is going to be the capacity on these edges? तो ये जो SI वाला edge है, इसका capacity I will keep to be the sum of the rho I. तो यहाँ पे जैसे sum of the rho I कितना, यहाँ पे तो सारे 1 है, तो ठीक है, इसका capacity मैं 1 रख लूंगा. So the capacity will be 1 everywhere. और इनका capacities भी मैं 1 रख लूंगा. ठीक है? Okay. What about the remaining edges? What should I keep the capacities to be? So let's keep the capacities to be 1 for these guys as well. Okay. So let us say this is my flow network. ठीक है? ऐसे एक flow network मैं construct कर लिया, right? So okay, again, just to make sure that every one of us are on the same page, how did I construct the graph? For every row, I am keeping a vertex. Right, Chintan, we will come to that. Yeah. So for every row, we will keep one vertex, which is the set R. For every column, we keep a vertex, which is the set C. Yeah. I have an edge between the source to every vertex in R. And the capacity of that is the row sum of that corresponding row. यहाँ पे सारे 1 है, but that's not necessary. ये 2 भी हो सकता था. Okay. Similarly, for every edge between the columns to the sink, I will keep a capacity that is equal to the column sum. Okay. And now there is these other edges, which is, suppose I look at the edge that is between the row I and the column J. Okay. Now what Chintan is asking, why don't I keep the values of this matrix as capacities? But see, that is not what I want. Okay. In fact, that is precisely what you don't want. Because अगर आपने उसका capacity उतना ही रख दिया, फिर तो आपका round up और round down करने की कोई जगह ही नहीं है. How will you round up or round down? That you should not do. But you should keep the capacities to be 1, which essentially represents the fact that the entry ij, that should not exceed 1. Okay? That is what this capacity 1 on these edges represent. That the entry corresponding to ij after you have performed the rounding, it should not exceed 1. That is something which we have to enforce, right? So these capacities essentially enforce this. Okay. Now here is the first question. I claim that there should be a flow of 3 in this network. There should be a feasible flow which is of value 3 in this network. Why can I claim this? So how would you, if I ask you to construct a value, construct a flow of value 3 in this network, how would you do that? Forget about algorithms. Just by looking at this example, how will you convince me that there exists a value of flow? Or let's say there exists a flow where I can send out 1 unit along each of these edges. So ये जो 3 edges है, नहीं, perfect matching. I'm not talking about integral flows yet. I am just asking you to give some flow. It can be fractional as well. See, because we don't know. I mean, ऐसे हमने construct कर दिया एक flow network. But how do I know that I can actually push 1 unit of flow along, out of each of these edges? So what is a feasible flow in this network? For all L equal to J. नहीं देखो ये तो आप no, but the question is, okay, so what I'm asking is, yeah, so I mean, I can assign a value of 1 to each of these edges, but how do I know that ये बीच में कुछ गड़बड़ नहीं हो जाएगा? You have to maintain all the constraints, right? You have to preserve the conservation constraints, capacity constraints. और ये तो it's a complete bipartite graph and all that. So how do you know that No, that's not. No, 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 no. The direction is always forward. That is fine. But okay. Yeah. See, the mean cut is also dangerous here, right? The mean cut. The problem with mean cut is यहाँ पे जो row sums है और column sums है, ये दोनों they turn out to be 3, right? But there might be an example where that is not the case. That can happen, right? Can that happen? So the question is, can it happen that ये जो capacity है और ये जो capacity है, they are different for some example? Okay, so some people are saying no, this cannot happen. So ये जो total capacity है outgoing from S and the total capacity incoming to T, then why should they be always equal? ये जो network हमने construct किया है, why should these two capacities be always equal to each other? Very good, Chintan. Yeah, they are basically the sum of all the cells. Absolutely right. So yeah, all I'm saying is it does not fall from the sky. There is a reason that this is happening. So the point is that ये जो outgoing capacity है S से और ये जो incoming capacity है to T, both of them represent the same number. What is that number? That number is either the sum of all the rows or the sum of all the columns. But what is the sum of all the rows? The sum of all the rows is equal to the sum of all the entries in the matrix. Similarly, the sum of all the columns is equal to the sum of all the columns in this matrix. Okay? So there will always exist a flow which is equal to the row sum or the column sum. Both of them are the same quantity, okay, in this network, right? And what is a feasible flow? Well, if you look at the edge which is for example ij, ठीक है, तो ये जो corresponding ijth entry है, suppose ijth entry is 0.2, so I can assign a flow value of 0.2 here, okay? So जो भी आपका ijth entry है in this matrix, उनका value I can assign that much of flow to the corresponding edge which is I to j, and that gives me a feasible flow in this network, okay? But the point is that is a fractional flow, okay? But now I appeal to the theorem which we had proved previously, that if there exists a fractional maximum flow, then there also has to be an integral maximum flow. The maximum flow in this network is, there is one maximum flow in this network which is integer. Why? Because all the capacities are integers, okay? So this is the crucial point where we are using this integrality theorem. So note that there exists an integral, और यहाँ पे integral का मतलब क्या है? Because all the capacities are 1, so integral मतलब है it's exactly 0, 1. So if you look at any edge, the flow is either going to be 0 or it's going to be 1. और कोई option हो ही नहीं सकता. Integral मतलब इस network में वही है. Yeah. Integral flow in this network. Okay. And that corresponds to a rounding. So this implies there exists a feasible rounding preserving row column sums. ठीक है, तो आपने ये नेटवर्क कंस्ट्रक्ट कर दो, अप्लाई योर मैक्स फ्लो एल्गोरिथम, या तो जो भी आपका आई जे एज में जितना भी वैल्यू है, अगर वो 0 है तो आप इस एंट्री को 0 कर दो, अगर वो 1 है तो उस एंट्री को आप 1 कर दो. But by the feasibility of this flow, you know that the row sums and the column sums will be still preserved. Okay, so this is nothing but a transformation of a fractional flow to an integral flow that you are doing. That's it. That's the proof that this rounding always happens, or this rounding will always exist. Questions? Why will the row sum be preserved? Shruti, the row sum is preserved because we are enforcing that using this capacity. देखो ये कैपेसिटी क्या रिप्रेजेंट कर रहा है? दिस कैपेसिटी इज एग्जैक्टली रिप्रेजेंटिंग द रो सम. अगर ये आयत रो है तो ये वन क्या रिप्रेजेंट करता है? दिस इज रिप्रेजेंटिंग द रो सम. तो आप तो यहाँ से 1 यूनिट ऑफ फ्लो ही भेज सकते हो, राइट? उससे ज्यादा तो नहीं भेज रहे हो आप. So which automatically means that the row sum is preserved. Now what यहाँ पे क्या हो रहा है? यहाँ पे it's basically distributing this value of 1 to each and every cell. तो जो आपका ith रो है, ये जो 3 नंबर्स है, बेसिकली ये 3 नंबर्स पे डिस्ट्रीब्यूट हो रहा है. ये जो 1 है, that is getting distributed to the different ij's, right, at this node. Okay, so given this matrix, you can always construct a feasible flow here by assigning the corresponding fractions to the to the edge ij. ijth entry agar 0.2 hai, so the edge ij can be made to carry a flow of 0.2. So there exists a fractional flow. Now, if there exists a fractional flow, then we know by Ford-Fulkerson there should also exist an integral flow of the same value. Yeah. So in fact, this is a general theorem as well. So if there exists a fractional max flow, there will always exist an integral max flow, given that the capacities are integers. Okay, further questions? Okay, so this is an example. Yeah, this is just to show you that, problems which have apparently nothing to do with flows can be reduced and solved using max flows. So this is one very nice example. Okay, so just I briefly mentioned that this same technique can also be applied. That's a good question, Kushal. So I tried to search for that. So the point is, when this problem was first formulated, that was quite a long time ago. So at that time, people used to publish census data. So census data, the way they were published, they could not somehow print the decimal part. So they wanted to print, round it or round it up or down to the nearest fraction. And that's where it originated. So this is like publishing census data. But I don't think that's a valid problem in today's world. But maybe there are some other applications. Yeah, I don't know really. But that's where it originated. Okay. Okay. So as I said that, yeah, this problem can also be extended if the row sums and the column sums were also fractional. So suppose they were not integers. So suppose, yeah, what is a small example? So maybe, yeah, instead of 3.14, this was 3.15. So फिर तो ये 16.1 हो जाएगा. This will also be 17.1 and so on and so forth. Yeah. So now the problem formulation will slightly change. It will say that again, you have to round up or round down to the nearest integer, but you are also now allowed to round up or round down the row sums and the column sums to the nearest integers. तो ये जो 16.1 है, उसको आप 16 कर सकते हो या 17 कर सकते हो. उससे ज़्यादा नहीं कर सकते. You cannot make it 15 or 18. Yeah. So it turns out that a very similar technique is also applicable there. With the only difference is that just the flow, the way we have studied flow is not enough. We need an idea which is known as circulation. Okay, so we have not covered circulation in this course, but yeah, for those who are interested, you can look it up. So if you use circulation, then you can also handle that particular case. Okay, great. So any other questions about this? ठीक है. Okay, good. So let's now move on to the next application that I wanted to show. And in fact, this is going to be an application of the mean cut problem. Okay. So by the way, how do I find the mean ST cut? So suppose I give you a capacitated network and I ask you to find the mean ST cut. How will you find it? So the question is, how do we find the mean ST cut in a capacitated network? Yeah, any idea? So we know how to find max flows. We can run Ford-Fulkerson, but how do I find the mean cut? Proof पढ़ा नहीं है किसी ने. So if you read the proof of correctness of FF, then this should have been. Okay. So let's go back one step again. So when do we stop Ford-Fulkerson? When do we stop FF? So what is the termination condition of FF? When do you stop the algorithm? Who remembers this? Very good. So when there are no augmenting paths. So when there are no augmenting paths, where? In which graph? When residual capacity is 0, well, residual capacity of every ST path is 0. Okay. So the answer is when no ST augmenting path in residual graph. Okay. So that is where you stop the Ford-Fulkerson algorithm. So again, the algorithm is very simple, right? So you start with zero flow and you augment, you find the ST path, you augment that flow. Then you find the residual graph. Then you again augment the flow by repeatedly finding ST path. When do you stop? Well, when you see that in your residual graph, there is no longer any augmenting path, augmenting ST path. तो आप S से नहीं पहुंच सकते वहां पे, S से T तक नहीं पहुंच सकते. So that is where you stop the algorithm and you declare that this is the max flow. The question is, how do you find the mean cut? What do you think is a natural way to find the mean cut now? Even if you didn't read the proof, what should be the intuitive? You run okay, so Vishwajit is saying you do a BFS from, no, Vishwajit, you have to make it more clear. What do you run? Where do you run BFS from? Okay, so I run a BFS from S, and which are the vertices that forms the cut? So remember, a cut is a partition, right? So some vertices will be on the S side, some other vertices will be on the T side. So which vertices do I want to keep on the S side? Very good. Okay, so what these people are saying, so remember what the point where we are stopping the Ford-Fulkerson algorithm is when there is no ST path in the residual graph. Okay, so now what you will do is find A, which is the cut that I want to find. A equal to all the vertices V such that V is reachable from S in the residual graph. Okay. Okay. So I just find the set which is reachable from S. Okay. The crucial point is, can T be part of A? Is T part of A? T is not part of A, right? By the stopping condition of the Ford-Fulkerson algorithm, T cannot be part of A. So this will imply that T cannot belong to A. Yeah, by the stopping condition of Ford-Fulkerson. By stopping condition. Okay. So now you declare A, comma, V minus A to be the mean cut. ठीक है? Why is this the mean cut? वो समझने के लिए you have to understand the proof of correctness of if. Yeah, it's not immediately clear that this is the mean cut, but it turns out that this is the cut which is of value that is exactly equal to the flow, and by the duality theorem we know that then it has to be the mean cut. Yeah, so please go through the proof. Yeah, even if not in all the detail, but you should at least understand why these things are true. Yeah, okay. तो ऐसे आप mean cut निकाल सकते हो. So you can find the ST mean cut in this procedure, in this process. Okay. Okay, good. So now what I'm wondering is, should I do the next application or not? Because it takes a bit of time. Okay, let's try. Any questions so far? Yeah. So either I can do a new application or I can go through something which you want me to go over again. Yeah, it's up to you. Yeah. Should I do the other application? Application. Okay. Okay. So the next problem, in the theorem, if there exists a fractional max flow, imply existence of integral max flow. All capacities have to be integers. Yes. This is very critical. So that's what I have been repeatedly saying, right? Because otherwise, the Ford-Fulkerson algorithm might augment fractional flow, right? Because the difference between the current flow and the capacities might have some fractional numbers. But agar sab kuch integers hai, then this is true. That's correct. Okay. So the final application is project selection. Okay. So what is the project selection problem? So given a set of projects, right? So you are given a set of projects that you can perform, and each project PI, each project I has a profit. Okay. So हर एक project का कुछ profit है, right? However, there are some constraints, of course. ऐसा इतना आसान तो नहीं होगा कि there is a bunch of project and you pick them. So there is a bunch of constraints which connects these projects to each other, and the constraints are what we call the precedence constraint. So precedence constraint का मतलब ये है कि there are some relationship of the following nature, that if you want to complete project say I, then you will have to complete the project J. Okay, and this is all represented using a directed graph. Okay, so suppose this is your graph. Okay, let me draw the graph. So I need some time to draw the graph. Okay. Yeah, that's enough. Okay, good. Okay, So suppose this graph represents this precedent constraints. Okay, so let me explain the semantics of this graph. So what these arrows mean is the following, that so suppose this is project I and this is project J. Okay, so the edge ij, it represents that there is a dependency of project I on the project J, which means that if you want to finish project I, then you have to necessarily finish project J. ये आप नहीं कर सकते कि you can finish project I without finishing project J. Okay. Similarly, if you want to finish, I don't know, this guy, say you want to finish this guy, okay, then you have to finish J as well and this guy as well. Okay, so suppose this is J prime. Okay, so if I want to finish, say, I prime, then I have to finish both J and J prime. Okay, so that sort of gives you a dependency relationship. Okay, is it clear to everyone? Now, what is the goal? So the goal is and the project, yeah, exactly, yes, and the project have a Y prime. So जिसमें जिससे भी उसका arrow है, whatever project it has an arrow to, you have to finish that project. Yeah. Okay. So what is the goal? The goal is to select projects to maximize profit. Okay, so you have to select a bunch of projects where you have to maximize the profit. Now this should be a bit surprising at this point because there is a trivial solution. अभी तक जो मैंने बोला, there should be a trivial solution to this problem. What is the trivial solution? So what is the trivial solution to maximize profit? Yeah, you just select all the projects, right? So far मैंने जो बोला, yeah. No, order, Shruti, so order is not that important. As long as you perform all of them, it's enough. Yeah, exactly. And then you so here we are not deciding really in which order to perform. That's like a topological sort of thing. But as long as you make sure that all the dependent projects you are picking, that's enough for the purpose of this problem. So I can select all problems. So clearly this problem is not so simple, right? There is a twist to this problem. And the twist is as follows, that the profits are not all positive. Okay, so ये जो red guys है, they have positive profit. Okay, so red have positive profit, positive PI, and the blue, they have negative PI. Okay, okay. So now is the problem formulation clear to everyone? So I have a bunch of projects. Some of the projects have dependencies on the other projects in the sense that you have to complete them before you can complete this one. Some projects have positive profit. If you perform them, you gain something, you gain money or something. If you perform some of the projects, then you will end up losing money. And you can imagine this can happen in several businesses, right? Some of the tasks which are not profitable, right? You can end up having a loss, but they are necessary to perform because maybe agar wo perform kar liya aapne, so you can then be able to complete a high profit project. Okay, so that's the decision that you have to make. And now the task is to select a bunch of projects from these projects, out of these projects, such that your profit is as large as possible. Okay, so is the problem definition absolutely clear to everyone? Yeah, any questions about the problem? So remember again, I don't care about, I don't have to spell out the order in which I'm going to perform them. That is a separate issue. But all I have to make sure is the set of projects that I'm picking, ऐसा नहीं होना चाहिए कि there is a project that you have picked, but you have not picked a project on which it is dependent. So if you pick I prime, then you have to necessarily pick J prime. But remember, and if you have to pick J prime, so in fact, this is a good example because if you pick J prime, then you have to also pick J double prime. Okay. So if the profit of J prime and J double prime is too negative, then you should not rather pick I prime. You should settle for something else. Okay, so now that is the non-triviality of the problem. Okay, so let's see how. So I don't think I have too much time, so I will give you the rough idea. Now I have a video on this thing, so I will upload that video. You can go back and watch it. So I created that offline, so it's a very detailed video, but at least let me give you the idea of how this is going to work. Okay, how are we going to use min cut to solve this problem? Okay, so here is the deal. Let me move this somewhere else. Okay, so again, I have to first design a network. So if I want to use max flow min cut kind of thing, I have to design a network. तो पहली बात तो है कि मुझे एक source sink चाहिए. So I introduce a source and I introduce a sink. ठीक है? What I will do is I will connect every source to all the positive profit projects. So I will connect the source to every project that has a positive profit. Yes. So a red project is depending on a blue project, right? So I prime is dependent on J prime. So the forward arrow means a dependency. Anything can happen. A blue project, I think you mean the opposite, right? Whether a blue project can depend on a red. Oh, yeah. Why not? I mean, let's just, this can also happen. Yes, this can also happen. So there is no restriction on those things. Yes. Okay, so I introduce an edge from the source to every positive profit. I introduce an edge from every negative profit to the sink. Every negative profit, every blue project to the sink. Okay, that's my flow network. Now, of course, this is not all. I have to spell out the capacities of these edges. Okay, now this is a bit sneaky. It's not immediately intuitive that why I'm doing it like this. So the capacities of the source to red guys, those will be the profits of this guy. Okay, so this is PI. Yeah. However, the capacity of the blue to T guys, any guesses what those should be? Again, wild guess. Minus PJ, right? And why do you think, okay, even, yeah, it's going to be minus PJ prime. And why do you think this is actually necessary? So forget about why this is useful. Why do you think minus PJ is necessary? If I keep PJ prime, then does it exactly, then it will translate to negative capacity. So I have to do this minus PJ prime. Okay, minus PJ, and so on and so forth. Okay. So this is how I define my flow network. Of course, now I have these other edges, which are the dependency edges, right? Which are somehow the dependency edges. Okay. So now let's, as I said, right, I will give you the intuitive idea now, and you can watch the rest of the video. So what I have already told you that I am going to use the minimum cut problem in order to be able to pick a bunch of projects. Okay. So what do I mean by that? What do I mean when I say that I want to solve the min cut problem? What I mean is, my expectation is, if I solve the min cut problem, I will get some cut, right? I don't know, some arbitrary cut. मान लीजिए this cut. Okay. Now, what I have to ensure that if I pick the projects that belong to the green side of this cut, so suppose this is the A side of the cut, I have to make sure that this is a feasible set of projects. Okay, which means what? Which means that ऐसा नहीं होना चाहिए कि A में ऐसा एक project है जिसका dependency है on a project which is in A prime. This I cannot allow, because if that happens, then this is not a feasible solution. तो अगर मैं mean cut use करना चाहता हूँ, ठीक है, अगर मेरा यही इच्छा है कि okay, I want to use the mean cut, और जो भी मेरा mean cut है A, that should give me a feasible solution, then I should rather try to ensure that there is no dependency outside A. Okay. Now you tell me, what is the easiest way to ensure that? How can I set the capacities of these of these remaining edges, the dependency edges, so that the minimum cut जो भी है वो edges को नहीं लेंगे. You see what I mean, right? So if I want to output the sets which are in A, then the cut should not be like that there is an edge which is going from A side to the A prime side. Okay, there should not be a dependency edge like that. Yeah. So what is the easiest way to ensure? Capacity 1, is that true? Capacity 1 है, फिर तो वो edge select हो सकता है, right? So when you are trying to find something that is small and you want to exclude something, then what do you make it? What should you make it? Should you make it capacity 1? नहीं, 0 तो नहीं कर सकते. See, 0 is a small number, right? So mean cut में तो 0 select हो जाएगा. Very good. That's a very good guess. So I will make these edges to be infinite capacity. I will make the capacities of these edges to be very, very large. Okay. I will make these capacities to be infinite, in fact. Okay. So think of infinity as a very large number. Yeah. It's much, much larger than all the profits in your input and everything, right? It's a very large number. Okay. So now here is a question. तो ये तो हमने intuitively कर दिया. हमने बोला कि ठीक है भाई, if you use capacity of infinity on these edges, then the mean cut problem will never pick a cut which uses one of these edges going across. ठीक है? This will never happen. But why is this true? Why should it happen that the minimum cut जो भी है इस graph का, that will never select one of these edges, or it will never select a cut which has one of such edges going across? Why do you think that should be the case? Or in other words, what is the maximum value of mean cut in this graph? Is the mean cut value in this graph infinity? Okay, Anshi is saying no. Why is the mean cut value in this graph not infinity? Very good. Very good. Okay. So what Vishwajit is saying that, hey, look, I have a cut which is of finite capacity. Okay. Which is not infinite. Which is that cut? Which is the cut that has a finite capacity in this graph? Exactly. Okay, very good. So if I look at this cut, right? Well, this is a cut which has a finite capacity, right? ठीक है ना? Which is another cut that has finite capacity. I claim there are 2 cuts that have finite capacity. I mean, at least 2 cuts. Exactly. So T and everything else. So if I look at this cut, yeah, that also has a finite capacity. ठीक है? तो ये जो edges को मैंने plus infinity कर दिया, now if I solve the mean cut problem, it cannot happen that the minimum cut will actually have an edge that is going from this green side to somewhere outside. ऐसा edge नहीं कर सकता exist, because I know that the mean cut value has a finite capacity. So this thing will never happen. Okay. This is the most important thing to understand. The rest is kind of just calculation, which I'm not going to show you. So you should watch the video. But is this point clear? Okay. This is the reason that we are making these capacities of these edges, of these dependency edges, to be plus infinity. Okay. Right. And now what I should convince you ideally is, okay, why does any cut in this graph, the capacity of the cut correspond to the total profit that you are actually gaining? So that is the last part, which I am skipping for now. So you can watch it in this video. Okay. So यहाँ तक तो हमने ensure कर लिया कि the mean cut in this graph, if I compute it, it is going to be of finite capacity and it's not going to keep any dependency edges going across. So it will be a feasible set. But now what I did not convince you is, ये जो capacity है जो cut का, why should this correspond to the profit of the projects that you are picking? Okay, so it's not very difficult, but it's not trivial either. It needs few lines of calculation, but yeah, I think I don't have time for that. So that's the thing. Yeah. Okay, so I will upload that video as well, and you can take a look. Yeah. So okay, so what I really wanted to policy time. So what I wanted to really show you today is that various problems which are apparently have no connection with flows, they can be actually reduced to solving max flows and mean cuts. So hopefully in your lifetime you'll encounter many such other problems, and yeah, you can apply in max flow. Okay. Yes, Varun. So I am just uploading, in the usual web page. So you can go out and check. So I have already uploaded a few videos from previous year. So for the part which I could not, when I was sick. Okay. You can't find because you did not look. Okay, maybe I did not publish it. Did I publish it? Okay, let me check right now.